In this video, we're going to begin a discussion on rates of change, which is going to be a really common theme for the rest of our course. Really what we're going to be doing is starting to scratch at this big topic in Calc 1 called the derivative. So let's start. We're going to talk about average rate of change and instantaneous rate of change. We'll compare these two things and try and wrap our minds around what they really are. And then we'll see if we can draw a connection between those rates of change with slopes. So we'll be talking about a slope of a secant line between 2 points on a curve and the slope of a tangent line at 1 point on the curve. And then finally, if we can find the slope of a tangent line, we'll see if we can find the equation of a tangent line right at the end of this video. Let's get this thing going then. All right, so the first question, what is an average rate of change? What do we really mean here? Here's a definition that I whipped up. It's not perfect, but it should give us a general idea of what's going on here. We're thinking about a ratio of an overall change in one measured variable compared to an overall change in another measured variable. Normally, we're going to be looking at the difference between things like a dependent variable over an independent variable, right? But we can kind of mix things up a little bit, even if we're not 100% sure about independence versus dependence. And then we're going to do it over this corresponding period. What does that really mean? Well, we're going to see what's happening when these are like connected point type things. This is going to push really far into a graphical interpretation quickly if I don't stop myself. But if we think about coordinate points, we're going to be looking at like a variable and another variable happening at the same point. Normally, we'll be thinking about this in points in time and things like that. But essentially, we're just going to make sure that they actually match up. For an instantaneous rate of change, we have a really similar idea, but this is instead a ratio of an immediate change in one measured variable compared to a corresponding immediate change. So we're not looking at some overall change over like a time period. We're looking at an immediate instantaneous change right now. If we think about this in a calculus perspective, what we're really doing is we're going to be talking about a ratio of an overall change in one measured variable compared to an infinitely tiny change in another measured variable over a corresponding period. If we want to loop that back to independent and dependent variables, this is an independent variable that we're going to change ever so slightly, and we're going to measure the overall change in the dependent variable. And it probably is a small change, right? If we're making an infinitely tiny change in the independent variable, we probably have a pretty small change in the dependent variable, but we'll look at that ratio then. That should sound like a calculus definition because when we talk about things like infinitely close, that should remind us about limits. Here are some examples. An instantaneous velocity could be measured by finding an overall change in a distance over some really tiny time period, right? An average velocity would be a change in distance over some relatively decent sized time interval. But if we just make that time interval really small, then we might get a hint at what the instantaneous velocity is. Similarly, an instantaneous growth rate of like a bacteria culture or something like that could be found by measuring the change of size in that bacteria culture over, again, an infinitely tiny time interval. An instantaneous rate of change of the likelihood of some event happening could be found by measuring the overall change in likelihood after an infinitely small change in a parameter. Wow, this example's getting weird, right? We moved from time intervals to something else. So this one is a bit strange, but here we have some likelihood function that's connected with like a parameter of a distribution or something like that. And if we change that parameter slightly, then we can go ahead and get, again, an instantaneous change in the likelihood, which is weird. Marginal profit could be found by measuring the change in profit due to an infinitely tiny change in the number of items manufactured and sold. This one's really strange because if we're thinking about the number of items here, it's not like you can have portions of a number of items, right? We say this is like a discrete quantity, like you have 1 item or 2 items or 3 items. So this infinitely tiny change kind of loses its relevance in this context, but we can still use it to estimate a marginal profit. Okay, so how does this connect to slope? Well, a slope is really just a change in a function between 2 points. So here's a slope of a secant line. For some function f, the slope of a secant line between 2 points, we'll call them p and q, is the ratio in the change of the y-coordinates compared to the change in the x-coordinates, right? We're used to this. You've seen rise over run before. Delta y over delta x, that's fine. For the slope of a tangent line, though, we have to be a little bit careful about this. For some function f, the slope of the line tangent to the graph of f at some point p is the ratio of the instantaneous change in the y-coordinates compared to the instantaneous change in the x-coordinates at that single point. That's kind of strange here, because now we're saying coordinates, plural, but we're only talking about one point. So there's really only one x-coordinate and only one y-coordinate. So we can't find differences like we normally would. Instead of denoting this delta y over delta x, we use these differentials, dy over dx, and we'll talk about that a lot more throughout the rest of this semester. That's some new notation. All right, so how are we going to approach this using calculus? We're going to think of a ratio of an overall change in the y-coordinates from some point P to a really, really, really close second point Q. So we're going to look at secant lines, but we're just going to make those 2 points really, really, really close, right? And we're going to move our x-coordinate just an infinitely tiny amount to get to that infinitely close point. And then we can look at the corresponding change in the y values. So you could think the slope of a tangent line, we could find that by finding the slope of a secant line between 2 points that are really, 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 really close to each other. And when we think about really, 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 really close to each other, we should be thinking about limits. So let's go ahead and do this. We're going to have an example of a function, and we're going to see if we can find the equation of the tangent line. Now, really, the main star here, the hero, is actually just the slope. All we really care about in this context is the slope of a tangent line. But once we have that slope of a tangent line, we'll be able to build the whole equation. This thing, though, is the hero. So let's go ahead and do it. We've got some function. We want to find a line that's tangent to our graph here at x equals 1. Let's just first go ahead and get a good sketch of this function so we can see what we're looking at. X plus 1 underneath our square root. This is a horizontal shift to the left, right? So this is our square root function shifted over here. And we've got an x value of 1. We're looking at this point. So if we're thinking about tangent lines, let's see if I can draw a good one. Oh, that's not very good. Let me see if I can fix it. A little bit better. All right, there we go. That looks like a good tangent line. This is the line we're trying to find. We're trying to find the slope of this line. What I want us to do first, though, is notice that the curve and the tangent line share a y value. It's the square root of 2. This point, 1 square root 2, is on both our blue function and the red tangent line. Let's just store that in our mind so we know this, okay? All right, so first we're going to find the slope of the tangent line, and then we're going to use y equals mx plus b, or point slope form, this or some version of this you might have seen. So remember, this point is on our tangent line, right? We got this y value here from f of 1, plugging 1 into our function, but that's on the tangent line too, so we can use point slope form or y equals mx plus b to find this once we have the slope. All right, again, the hero here is the slope, so let's go ahead and find the slope. M is going to be the slope between 2 points getting really, really, really close to each other. So I'm going to set up a limit, and remember up there we said we're going to make the x values really, really close. So I'm just going to say, well, I have one x value that's 1, and the other one is just going to be some unknown value x that approaches 1. And now what I need to do is find slope, delta y over delta x, right? But we're not going to use delta y and delta x. We'll go ahead and just use the difference of the y values. If one of our x values is x and the other one is 1, then the y values are f of x and f of 1. So this is f of x minus f of 1 over the x values, x minus 1. Notice this is just difference in y over difference in x. But since we know what this function is, we can go ahead and set up a limit that we likely have seen maybe before, or maybe at least something similar to it before, right? Notice that if we first hope that, yeah, everything's going to be continuous in the numerator and denominator separately, we could just plug things in. We're going to get some indeterminate form, 0 over 0. So remember, warning bells should be going off. We're going to have to do some sort of algebra. So the algebra that we're going to do is we're going to use the conjugate, right? So let's go ahead and do that. I'm going to multiply on the top by x plus 1 under a square root plus the square root of 2. And I'll do that same thing on the bottom. And if you've done this for a little bit, you shouldn't have to think too hard about doing the distributive property on top I want black here for my parentheses. There we go. Because this is going to end up being a nice little pattern when it multiplies out to give us a difference of squares. So we're going to have a limit as x approaches 1 of x plus 1 minus 2 all over x minus 1 times square root of x plus 1 plus the square root of 2. X plus 1 minus 2 is conveniently x minus 1. So look at us go. We've got an x minus 1 on the top, an x minus 1 on the bottom. We are allowed to cancel those things. And even though we're going to end up with a different function technically, because the domain of our function is going to be different, the limit will end up being the same thing. Because remember, the domain's only different at that x value of 1. And when we talk about a limit, we're never actually going to get to that x value of 1. All right, so now what we've got is 1 over the square root of 1 plus 1 plus the square root of 2. Or this is, 1 over the square root of 2 plus the square root of 2, or I'll just call it 1 over 2 root 2. It's kind of ugly, but that's our slope. All right, neat. So now let's go ahead and set up our equation of our line. Let's remember we know a couple things. We know we have a slope of 1 over 2 root 2. We just found that. And we also had this point, right? 1 comma root 2, because remember the tangent line and the function crossed at the same point. That was how we defined our tangent line. They have that same point in common. So what I might do is say, like, I have this specific x value, that's 1, and this specific value of y, that's square root of 2. I'm a point slope person. Whoops. So I'm going to use that. So I'm going to say y equals 1 over 2 root 2 x minus 1 plus root 2. I can do some distributive property here, and I've got 1 over 2 root 2 x minus 1 over 2 root 2 plus the square root of 2. This is kind of like an ugly thing. If you want, you could add these fractions by making common denominators, right? We could divide by 2 root 2 and then also multiply by 2 root 2 here. And then we have a common denominator that we can combine these things in. So this is 1 over 2 root 2x minus, well, let's just put all this stuff together. I've got a 2 root 2 in the denominator. This numerator here, I have a root 2 times root 2, that's 2, times 2, so this is really 4. So this is negative 1 plus 4, so that's going to be plus 3 up in my numerator. There's my linear function. If you wanted, you could just call this x plus 3 over 2 root 2, right? Common denominators, combine those things together. That works. It's pretty ugly, but that is the equation of that red line. If you wanted, you could use y equals mx plus b, and all you would do differently is you'd say that's x, that's y, there's your m, 1 over 2 root 2. So you just go ahead and plug everything in, and you're left with one unknown thing, and what you'll get is 3 over 2 root 2 as that b y-intercept, and there you go, mx plus b. No big deals there. All right, so again, the main hero here is this idea of instantaneous rate of change or instantaneous slope that we can find by setting up this limit. These limits are going to look kind of familiar because we've done things like them before, and in the future what we're going to do is try and really understand these specific types of limits, which we'll come to know as the derivative. But that's all we've got for now. In the future, we'll look at that a little bit more in depth, but hopefully this is helpful to start.